we will have another lecture, one more lecture to cover the balancing car, and I think we are pretty much 80% done for the introduction part of the balancing car. Since I'm assuming you have done your done with the wireless communication, right? So after this one, after part 2, if you can let the car get balanced on the table, then you just need to merge your wireless communication, that joystick, that piece of sketch into this one. And there will be a lot of debugging, I'm pretty sure, for a couple of weeks. And then wrap it up. You'll get a product. Is that exciting? I know that won't be that easy, but let's get through the most difficult part, which is the PID control. Takes me a while trying to understand his code, and eventually I found out it's totally not necessary to make it that difficult. And I simplified his code a lot, and finally it worked. I forgot, like 2 to 3 weeks. Because the control theory here is pretty new to me. I was not a mechanical engineer, and you know, robotics is normally in the Department of Mechanical Engineering in other universities, in University of Utah, and actually everywhere for the big ones. They in the computer engineering, they don't have robotics programs. Normally in mechanical. It's also called mechatronics sometimes. But I think this is really cool. I mean, for some of the mechanical engineer students, I don't think they can get that deep into the microcontrollers like this. Yeah. It's good to know these things. Okay, the control theory is really interesting. So here's one thing. I'm not sure if there's. I think I'm sure there must be some other alternatives you can use, some other methods you can use to make it work in the same way. If you find out, let me know. But this is a way I have been found working really well. Let's get it working, make it work first, and then try to improve it later. So we were where? We were, I think, somewhere here, I think, right? So this is it's called a data fusion. And remember, in your MPU sensor with your Arduino microcontroller, you can get the angle from either the accelerometer or the gyroscope. Remember that? If you look at this one, because this is 1G, perpendicular to the ground, or table surface is 1G. So you just need one parameter, which is the Z direction, the acceleration on the Z direction, and divided by 1G, and then use the A sign signal and convert into a degree. So you get errors every time. So the setup point definitely is angle 0, right? So when you have to use your hand to hold it perpendicular to the table surface real well after you part it up, and you hold it there, and it's going to start calculating. So we get a little offside angle from the gyroscope. And every time you calculate it, again, you get another value, and you minus, subtract that one. And if the reading every loop is the same as the angle offside, you're getting zeros. Okay, so if you set up that angle to be to be the setup point. So the setup point should be angle 0. Because that's the offside signal. So whenever the angle is not 0, which means it's leaning forward, backward, so there will be a little delta theta created from the movement, and that's going to be the error you are going to use for your PID controller. You have to tell the car at the very beginning what is the 0, and so the error is 0 at the very beginning, which is like you just hold it, stand up on the table surface. So here's one way to calculate the angle, right? And using the accelerometer, and also for the gyroscope, there's nothing about G. Okay? So just to calculate the dynamic change of the angle using the, I think it's what's the unit? LSB per degree per second. Where is that one? Oh, it's on the previous page. But anyway, so we calculated, right? Remember in the last lecture we calculated. So here's the equation to calculate the gyroscope's angle, and that's the equation to calculate the acceleration's angle, accelerometer's angle. Is that frustrating? It's like since you forgot what I did last time. So that's the acceleration's data, the raw data, divided by 8,192, right? That's what you set up in the register. So it's going to be how many G's you have. Divided by 1G is, divided by nothing. So, or you can treat this guy as 1G. So divided by 1G, and then times the 180 degree over pi. Okay, so which is this number. So that's the angle in terms of acceleration. And if you use this one, you can calculate the gyroscope's angle, because here's the gyroscope raw data, and this number is calculated by what? Let me see if I put it here. All right, so it's in part 1. Also, it's in the notes here. Let's take a look at the notes. The raw data is a binary number. You can also say that's how many LSBs. Gosh, every time it's loading PDF is so slow. That. Here, 4 milliseconds is a time for each loop, and you set up this register as 131 LSP per degree per second. Okay, so that's why you want to do this calculation, and this one divided by this number is giving you this. That's how this was calculated. So definitely in the code, you have to include this one in here in order to get the angle. That's for the gyroscope's angle. So this one, I didn't find is super necessary. If you comment out this line, it's still working. But a lot of people are suggesting you probably want to add this is because you can see it's actually a different weight for these two angles. And they're trying to use it's a high pass filter, this is a low pass filter, and fuse these two data in together to get an overall angle, to get rid of the drift of the gyroscope angle. You could actually feel that physically. You can, so let's do that. Let's try include this one or not including this one. Then let's see what's the difference between these two. I think eventually you probably have to do this. Since I have seen every single tutorial regarding this balancing car or using a gyroscope, you do need a data fusion. But I don't have actually a numerical analysis or plot to show you, like, if you don't do this, how unstable the system will be. I don't know how to present it. I can think about it, but because it's given and it's been working, so the goal is just make it work first and combine with your wireless communication code. Let's get it done first, and then we start improving it. Okay. So directly use it because it's given. So you get an overall angle. Here's the angle, and you can use that angle minus the set point, which is 0. So actually, it's going to be this angle itself will be the PID error. Will be the angle error, not the final PID output. Okay, that's going to be the error for the PID controller's input. So which is here, here. Okay, and then let's go to the code. Okay, so all the ones on the top has been explained, so nothing special until here. So we are here. So this fused angle data minus 0 will be the error. You don't have to write a minus 0 here, but you should just know that's the error input for the PID controller. And now then just do a PID controller calculation according to the equations. So there's one thing I think you have to use, which is you want to confine the PID output within 400. So it's not going too large or too small. So it's gonna like rotate the wheel like crazy. That's something you want to use. I think I tried do not confine the PID output within this range. It's not going to work really well. So definitely do that. And also, there's another thing here. It's pretty important. Whenever the angle or the PID output is within plus minus 5, so actually the error is super tiny. You don't want when the car, because you can never make it perfect. So when the car is almost perfect, balanced, you don't want to do any adjustment anymore. So the car is not like always shaking, right? So whenever it's within that range, you consider that the car is balanced and do not do anything. So the PID output should be 0. That's critical. If you don't do that, the car will shake all the time. It won't stay there. So here is a critical part. It's pretty difficult to understand this. Let's take a look. All right. So that's the PID output, but you have to process it and convert it to another parameter here. And that parameter is being used as a parameter to compare with the counter inside the ISR in order to drive the motor. Let's see how that works. I'll make sure you guys understand this. Okay. So ISR will be triggered every how many microseconds? 20 microseconds. We calculate it. We design it that way. Okay. And every 20 microseconds, it's gonna jump to here and add 1 to the counter, right? So for example, this parameter is calculated from the PID output. It's pretty big, okay? And let's don't think about why we have this here. Okay, let's just look at the overall structure of the ISR first. So it's going to add 1 to the counter, and it's going to compare the counter to this number, which is pretty large. And definitely at the very beginning, the first time it enters this SR, it's not going to satisfy this statement, right? So it's going to skip this if statement. Take a look. If blah blah blah, if else blah blah, if is here, and then else if done. That's the ISR. So if this is not satisfied, it's going to come to here and run these 2 lines, because you can see counter if counter equals to 1, which is exactly the first time it enters the ISR, right? The first time it enters the ISR is going to be 1 for this guy. So satisfied, and do this. So take a look, what is this? Pretty soon, okay? And then the next time, the next 20 microseconds, it enters this SR again. So this counter becomes 2, and this is still not satisfied, and this is satisfied, and then do this. Okay, and keep going. But at the third time, this 2 will not be satisfied anymore. Okay, so this number becomes larger until it satisfies this condition. It's going to execute everything inside the if statement. So the first thing is to clean this out, reset it. We can start over again. And then do all these things. So I'll let you know. So this part, you will get into there first, but let's look at the structure first. So this part does nothing but just set up the direction of the 2 wheels. For example, if the car is leaning forward, it's going to rotate the wheels to this direction. It's just setting up. It's not rotating anything yet. Just set up. Okay, this direction. If it's leaning backward, so it's doing a judgment here. If PID output is negative, right? Else, because this is positive, so else will be negative. Then it's going to rotate into another direction. Okay. Yeah, don't think about too deep about the like port D, like blah blah. What is that? So no worries. It's just doing like if the PID output, the angle error is positive, then rotate that way. If the angle is negative, rotate that way. But it's not rotating yet. It's just setting up the direction, make it ready. Okay? All right. And then the motor, this counter next time. So after it satisfies this, you know it's being reset immediately after it enters that if statement, right? And then it's going to make the wheels ready to rotate in a specific direction. And then get out of this, all right? And do nothing because counter is 0, but the next 20 microseconds is come back to this SR again, the counter becomes what? 1, right? Because it was reset here, and then the next 20 microseconds is adding 1 to it. All right, so it's going to satisfy this again. What's going to happen? Just do this. Okay, do this, and then the next time it's going to be 2, and do this. All right, so that's how that works. No worries, what's inside, okay? Let's think about this again. What's happening for the overall structure? The ISR will be triggered every 20 microseconds, right? It's like you have 4 milliseconds over here for the loop, main loop. And every 20 microseconds to trigger ISR, do this, which is this guy here. Like, okay? And this SR actually controls the wheels. It rotated and also defines the direction of the wheels. So it is able to balance really quickly, since it only takes 20 microseconds to make a judgment. And every time it enters the ISR, it's going to add 1 to the counter, right? But at the very beginning, it's not going to satisfy the if statement. It's going to go to the bottom 2 lines. So I will let you know now. So this is providing a pulse, a rising edge, and a positive pulse to the step pin. And the second line is going to pull it down. So what these two lines doing here is actually just create a pulse. So a pulse means one step, like this. So in that case, it takes 20 microseconds to get it to the ISR and add one to the counter. So it's not ready yet, right? Then do not get a step. Whenever it is ready, move a step. Okay? So now let's take a look at this parameter, which is the critical one. So the counter is increasing by one every time, every ISR, right? And it's comparing with this parameter. So now let me know. Let's take a look. If I draw it here, so 20 microseconds, it's not doing anything. 20 microseconds is not doing anything until it satisfies that condition. Boom, boom, boom. Right? And then keep doing this again. So let me know if that parameter here, so that represents one step. Because this pulse, this pin is connected to the step pin of the driver. So this is the one step, either back or forward, depends on the definition or what you configure inside here, which is defining the direction of the motors. All right, so here's a question. That's a parameter you are comparing to with the counter. And if this number is larger, okay, are you going to have a faster motor rotation or slower rotation? Why? Taking more loops to what? To get one pulse. That making sense, guys? Okay. So what's actually happening here is, depends on that variable, you are making 20 microseconds plugs into the steps controlling signal. If there's one more number in that parameter, you are getting one more 20 microseconds into the driving signal for the motor. All right. Now let's come back to take a look how that parameter is calculated. So now we know how the ISR works. And so that's how that one is calculated. It's a little bit empirical, but let me explain to you so you know why. All right. I think the balancing car is the most exciting part of this course. I mean, getting frustrated because it's too hard. All right, so let's take a look at this one. So the parameter is calculated in this way. Let's don't look at the code right now. So I'm going to write something down on the paper. Let's take a look. So the number of these 20 microsecond plugs, I will just name it as X. I don't know how many, but X number of 20 microseconds plugs in there. And you'll know that the frequency, so this signal, eventually, you are going to get a frequency which is 1 over T. You agree with that? I don't know how frequent you are going to get a step, but what I know is there will be a period, because next time there's another pulse. So this part is going to be T, and the frequency will be 1 over T. You agree with that? Okay. So the adjusted frequency f prime equals to what? If you have one more 20 microseconds plug into the signal. So every 20 microsecond plug is a logic low, right? But no matter what it is, you're adding that 20 microseconds to the T. So if you have one more 20 microseconds to be added to the T, what's f prime? Or x amount of 20 microseconds. I can replace this guy as x. All right. So what's the unit for this one? What's the unit? I know it's frequency, but if I say this is how many steps per second, do you agree with that? All right. How many steps per second? Or how many pulses per second? It's the same concept. That's the frequency of the pulse or the frequency of the step. So that's the unit for this guy. And the wheel has the R, and the parameter of the wheel equals to 2 pi r. You agree with that? So if you have a different wheel, you probably need a different parameter here. So P equals to 2 pi r, and P over 200, what is this? So 200, you have 200 steps, and P is how many meters per, just how many meters, right? That's a parameter of the circle of the wheel. So this is meter, this is steps. So you are getting how many meters per step. Is that correct? And then you multiply this by this, and you are getting f prime times p over 200, and you are getting this times this, steps per second times meters per step. What's the final result if you do this? Okay, so you can convert the you can convert your x, how many plugs you have, to meters per second, which is the real displacement will be made by the wheel. So that's from the input to the output. Okay, you need this transfer function. So eventually, f prime is 1 over t plus x, and p over 200. So this equals to, I mean, it's pretty close to something, because this, if you ignore this one, compared to x, can be a little bit smaller. So it's close to something like this, times a constant. We'll say a. So that's going to be meters per second. You want to make it linear. So whenever you have a 1 degree difference, and you want to create a 1 millimeter displacement. Okay, so that's one degree difference. However, if it's 200 degree difference, it won't be 200, but let's say 5 degrees, and you exactly need 5 millimeters, but not 10. So you need something to make it linear. Okay, because the mechanical system is not linear at all. You can see that, where is x? Denominator, right? It's not linear. Whenever you get a 1x and you are getting something else, it's going to be a curve like this. So what's going to happen is whenever the angles are changing slightly, it's moving slightly. But whenever the angle changes a little bit more, it's getting a larger range of swing. I know it's hard to understand, but so normally the way to convert the PID controller's input into whatever output, and you want to make it linear. So whenever you have one more error here, you just add one more output, one more to the output. 2, 2, 3, 3. Okay, but not like 1, 1, 2, 10. Okay, so that's something wrong. So it's frozen. It's frozen. Okay. It's not critical here if whatever A is, totally not. The critical thing is you need to have the reciprocal of the input to be used as your PID controller's input. So if you look at the code here, it doesn't have to be this. I think this is a pretty empirical number here, but the key thing is you have to put this number in the denominator to make it work. It doesn't have to be +9, +8, +7, or nothing. I think it's going to work. I think I tried it. It works. But you do need a little gain here. Because the units are being converted, so somewhere around this number will make it pretty smooth. It depends on all the numbers you tried out. That's not super critical. It doesn't have to be 5500, but you have to put this number in the denominator to make it work, right? To make it linear, relatively linear. I will give you a few minutes to think about this if you have any questions. If you are used to it, I know this is pretty new. This is different from what you learned in system control and circuit tool, all the series equations. I mean, if you have any better way to explain this, is in the use the terms in system control. Have you had anything similar to this? Practically, in real world? Yeah. It's using an ISR, and ISR is being triggered at 20 microseconds. So this is given. Think about it, this is given. And how can you utilize this for your PID controller? So use a counter and use the number of delays to be plugged into the stepper motor, the stepping trigger signal. Okay, that's from the input to the output. Probably you are thinking, why not directly, if you have a large angle and through a transfer function, just give a faster speed? Why not? Think about so this is just making everything complicated. It's not straightforward. You have to think about everything here and trying to understand it. And it's not even the original code from that guy, from the guy who invented this balancing card. It's a lot different. I mean, this is like 3 times shorter than his code. It's working the same way. It's not making sense to like confuse people in that way. This is more straightforward. So I have been thinking about this the same way. Okay, it's just the system very simple. Whenever the angle is larger, you need to give the faster speed to the wheels in a specific direction. So what's the potential issue for that? I don't know. I don't know the answer. Let's think about it. Let's brainstorm on that. Yep. But what's the difference? I mean, compared to this one, though. But you can have all this just tune all these PID gains to avoid that, right? I mean, I didn't try it. Maybe that's gonna happen. But is there any way to think about this intuitively? Like, why is that not going to work? So if you do that, sounds like there's no, you don't even need to interrupt, do you? You just need a one loop, and you can define it as 4 milliseconds, but it's too long, right? It's too long to trigger the wheels. It takes from 4 milliseconds too long. So probably want to trigger the wheel more often, right? So it's better to have a um, ISR there to be triggered more often. And it's more independent to everything here, since you probably will have the remote controller to be plugged in there, and the PID controller's calculation, which includes all the divisions, which takes all the time. And if you don't do that, oh, that's probably why the robot car didn't work really well last spring. You know, I should use ISR over there. You were not there. That's for the junior design class of May Stover. Yeah. So you probably want to use ISR to rotate the wheels. All right, so that's given. We have to use ISR since it's going to be triggered more often, like what we desire, and it's not being affected by anything else. It's more independent, right? Okay, so that's given. We have to use ISR, okay? And if you have to use ISR, what do we want to put in ISR for to adjust the movement of the wheels for this purpose? I mean, definitely you have the main loop to calculate the angle errors. No problem. That's pretty simple. Like just use all the code provided. So definitely you get the angle error over there, and use that parameter to guide your PID controller's output. If you do not have this kind of 20 microseconds plugs, like something like this, what you can do? Are there any choices? So you get an angle error here. It's a main loop. Angle error, triggered, move the wheel. If the error is larger, you get into ISR. How to think about it? We, so the largest one, if you look at the limitations, the largest one is 400. So it's plus minus 400. So I assume it's going to be 10s to 20s. The maximum will be 400. So the issue here is whenever the ISR is triggered, how can you utilize the angle error as information to drive your motor there just within 20 microseconds? How? Yes, I think you can get it. Yep. Different different step. I think it's worth to try. Mhm. I tried a couple ways to do that. The straightforward way we just talked about didn't work really well. Mm. It's gonna take a while to master everything here. Since we couldn't visualize what's going on for all these different all these changes whenever the wheel is moving. But we can definitely probe the step pin, right? But I'm pretty sure it's gonna be a like PWM or something. Sometimes it's more frequent, sometimes it's wider, and with the pulses, like keep adjusting like this. So that's a good way actually. So because this is working, and if we probe the step pin to the oscilloscope, and whenever the car is balanced, you will visualize all the pulses, how the pulses are moving, like getting wider, getting narrower. It's going to be a certain pattern. And if you use the way we just mentioned, if the angle is larger, getting the ISR just get more steps. Then look at the pulses again and see what's the difference between these two. That can be somewhere you can get more information into it. Um, and also definitely look at the set point, the angle data. Okay, just plot it and see the line data and see how stable it is. Yeah, I think we can change to another angle and to take a look at this. But I think the strategy now here is if this makes sense, let's go ahead and use it, combine with your wireless modules. Let's get that one work first. Before we, so if it doesn't work eventually, for example, it's not being stabilized whenever you add that remote sensor in there, then we can start looking into it. But I would put that one as a last or lower priority for now. To think. Mm. Mm. Whenever it's available, then you do something. Otherwise, don't do that. I was talking about the remote controller. Yeah, I think it's only trigger whenever you get something. Is it? If you look at the code. Yeah. Yeah. Uh-huh. Yeah. Yeah, I think it's being balanced by SR. So no matter what you are doing here, it's always being balanced. Even though it's moving, so the moving part is being executed in the main loop. But whenever it's moving, it's still trying to balance itself in the ISR. So it's like doing this one, but doing this quickly, but you just couldn't see that. But actually, it's doing that. because the movement is pretty slow compared to the ISR. So if you divide every single movement into 1,000 static pictures or frames, it is able to balance itself during every time frame, which is 20 microseconds. Is that amazing? I think that's why ISR is important. Whenever it's doing something else, it's still able to check the balancing status every 20 microseconds and make it balanced. Only when the speed of the car is as fast as 20 microseconds, that frequency, comparable to that, then it's gonna be hard to tell. But I think it's like 1,000 times less. So the PD, this is another way to write the port, to assign values to the port. It's being used in the old microcontrollers, but it's working here as well. So I think you have A, B, C, D, all these number of ports, the name of the ports. When I was in college, the teachers, I couldn't remember anything I learned from her, but I can only remember like she said, port D, blah blah blah, port A, blah blah blah. This is the only thing I remember, and I didn't know what are they. So they're just IOs, right? So the D, they just name it as D. How many? 8. So from number 0 to number 7. So totally you have 8 ports IOs for D port. And you can assign the values for the D port in parallel. So on your microcontroller, there are, for example, the 8 digital pins. You can directly write port D and equals to 0B, which is the binary number, like 0000. Then it's going to assign a parallel 8 zeros to port D, which is D0 to D7, right? Boom. Okay, so you can assign everything at the same time. And for this OR logic, so the reason you have to reset every single bit for the D port is so you can do a OR logic after that. So you have to clean out whatever was there first. There might be a one somewhere, right? You just want to clean all the D port to zeros, all zeros, and then you can start manipulate every single bit. Just use the OR logic. So that's why you do this. Then it's gonna cite this pin. I think this is 765. So D5 to 1. So D5 is being shorted to the direction on the driver. So these 4 pins are being used for the number of steps and the direction for the 2 motors. So if you look at here, D is direction, S is step. And so these 4 bits are DS, DS. So the first DS controls the D and S for one motor on one side and the other one on the other side. So if you look at this one, so this specific pin here being set to 1, right? So you can tell me this is for what? For direction or for speed? For step? Direction for one of the motor, right? And this is for another motor's direction. So you can tell they have a different direction, which makes sense, right? Since you look at this side is counterclockwise, this is clockwise. So they have to be the different direction in order to move in one direction for the car. And if you want to change the direction of the entire car, here, see, whenever the angle is positive, you do this. 0, 1, right? Otherwise, you do 1, 0, 1, 0. Make sense? So it's leaning forward, leaning backwards, and 1, 0, 0, 1. So literally the if statement block here didn't do anything but defines the direction of the motor. This is doing, so digital write is on only one pin, I guess. Yeah, I think this is pretty convenient. I'm pretty sure there's another way, but this is convenient. Let's just use it. You can do digital write here, digital write the other one, right? Just do, but you couldn't manage all the 8 ports at the same time. So you probably want to, you just need 4 of them. But if you do 8, then all of the 8 ports will be changed at the same time. Why not? It's not doing anything wrong here. If you do pong pong, probably there will be a delay. They won't be synchronized, right? Digital write, digital write. If you do 4, digital write, digital write. So it's going to be a delay in between. It's pretty short, but it's not ideal. Mm-hmm. No worries. It takes time to understand everything. It took me quite a while to understand his code and simplified everything to this version, which worked. Um, so no worries. So I'm here to help. Another thing is, whenever you find something like this, if you don't understand right away, just treat this guy as your girlfriend. Just look at her every day, every second, until you understand her. Even though she's moody, but understandable, because this is so cute. This works, right?